Welcome to today's video where we will discuss what are called piecewise functions. We will look at how to do function notation calculations using piecewise functions, and we will examine how to graph piecewise functions. Okay, so let's have a look at what does a piecewise function look like. So here's an example of a piecewise function. So piecewise functions are essentially functions that have multiple behaviors depending on what type of an x value that you choose. So if I look at this function, it will do either this or this, depending on where the x value is that I'm substituting. So what it says is if x is less than or equal to 2, then I'd use this piece of the function. If x is greater than 2, then I'd use this piece of the function. So if I just look down below here at the question 1, which says find f at 1, well, you don't go and put 1 into both of these. You figure out where would 1 fit in these intervals over here. Well, the number 1 is less than or equal to 2. So that would tell me f at 1. Let's get my pen here. So f at 1 should equal, replace x with 1 and add 3. F at 1 should be 4. If I did f at 3, this is x, remember this is f of x, so I'm replacing x with that number. So if x was a 3, x would be a number that's more than 2, so I'd use this piece of the function, which would be 3 squared, take away 2, 9 minus 2 is 7. If I did f at 2, this would be if x is actually equal to exactly 2. Well, if x is equal to 2, I should use this piece of the function, which would give me 2 plus 3. F at 2 should be 5. Now the next thing we're then going to do is look at how do I graph these. We're going to limit you to just either linear, so this would be a linear relation, grade 10 graphing, and this would be a quadratic function, which would be grade 11 graphing. It'll be some combination of linear and quadratic functions. Okay, so if I took this function, and I just go down here, I'm just going to maybe take a copy and paste of this. I have it down here. Actually, let's go to the next page here. And I paste that here, so I have it to look at. All right, we'll put it up there out of the way. Basically, what I'm going to do is graph two different graphs. I'm going to graph y equals x plus 3. And then I'm going to draw a graph of y equals, remember f of x is the same as y equals x squared subtract 2. And we're going to use the knowledge we would have accumulated in these prior courses to graph these. Now one thing that you must do, I'm going to use tables of values here, and some other details, but I'll get to those in a second. I call these your boundary numbers. So at the number 2, this function is switching behavior from this to this. I'm going to have to see where is the function at that particular instant. And then, based upon whether you have an equal sign or no equal sign, you'll determine whether you put an open circle on your graph or you shade it in at that particular point. Well, let's have a look. So let's start with, you always start with the boundary number. So I'm going to put a 2 in here. I'm going to put 2 in here plus 3, I get 5. Because it's linear, one more point should do it. Pick a number that's less than or equal to 2. So you can't just pick any number you want, it has to be a number in this interval. So I'm going to go with 0. That's less than 2. Put 0 in here for x, 0 plus 3, and I get 3. This one's good to go. This point is going to be a solid shaded in point because there's an equal sign. This will be my second point to give me that graph. So why don't we just, well, let's get my graph started here. So 1, 2, 3, 4, 5, 6. Now normally I do the two of them first, but I want you to kind of get a sense of what I'm doing here. So basically I'm going to graph this on a number line, and I'm going to go to the ordered pair 2, 5. So 2, 5, 2, 1, 2, 3, 4, 5. And I'm going to put a closed-in dot. That's the boundary number. And then I'm going to put 0, 3 on my graph. So 0, 1, 2, 3, which is also, anything inside here is always a solid dot. The only time you're ever concerned about whether it should be open or closed in is right at the boundary number. So in this case, 2 is our kind of number we're worried about. Now, because this is linear, it should make the pattern of a straight line. I've got enough points here that, and it keeps going forever in that direction. Now, what students will do wrong is they'll put an arrow on this end as well. Well, the problem with doing that would imply that this goes way past here. Well, it doesn't, though. It only does this, the linear relation x plus 3, if x is less than or equal to 2. So you can't put an arrow on there. You can put an arrow on this end because it goes forever this way. But you can't put that arrow on the right end because it doesn't go forever in the other direction. All right, let's go to this other one. So this is a parabola. So I know it's U-shaped. I know it opens up because it's got a plus sign in front of it. I would always identify where the vertex is. Now sometimes you can use the vertex, sometimes you can't, just depends. This one would have a vertex, so it has nothing added or subtracted inside the bracket here with x, which is being squared, so it's going to be at 0, -2. So the vertex is at 0, -2. Now, the x value at your vertex is 0, right? That's your x value. I'm not going to be able to use that point. Because if the x coordinate is 0, it would actually be working like this, linear instead. So there's a point, but I can't use it. But it gives me a sense of the shape of the graph. So I just keep that in mind, even though I can't use it. Let's start with the boundary number. Now students will get confused here and say, you already used 2 over here. I understand that, but I still have to put it here as well. Difference being this time I'm going to represent it with an open circle. 2 squared is 4. 4 take away 2 is 2. Pick one more number. Let's go with 3. 3 squared is 9. 9 take away 2 is 7. All right, now over here on the same grid, so I've got to kind of color code it. I'm going to start with 2, 2 is the endpoint of this one. So over 2, up 2, put an open circle. Pick one more point. Now you've got your 3, 7. So just go back to red here for a second. So there's 3. Remember this was 5. This was lined up with 2. Oh wait, no. 1, 2, 3, 4. What the heck did I do? This is not in the right spot. 2, 1, 2, 3, 4. That wasn't high enough. My blue graph here, I kind of messed it up a little bit. This was actually... So 5 is way up here. So 1, 2, 3, 4. This was 5. This is 7 up here. So my blue graph, if I just fix that up a little bit, if I can, I'll try. Erase it. So this is not quite the right slant to it. Get rid of that. Alright, so my 2 points here, if I just go back in, 2, 5, so 2, 5, back to blue, 2, 5 was there. Then I had 0, that was still right, 0, 3. Then I would make my straight line as best I could, and it would go forever in that direction. Now, I've got my open circle here at 0, -2, or sorry, 2, 2. That was open because there's no equal sign here. I picked another number that was bigger than 2. I went with 3, 3, 7. So 3, 7 is here. When you arrive at Pre-Calc 12A, we're assuming that you've gone through NERF, Foundations 11, Pre-Calc 11. You have to have some prerequisite skills, being graphing. If this wasn't piecewise, this would have come down. Remember I said the vertex was at 0, -2? Your vertex would have been down here. But imagine that there's like a force field here that won't let you go past there because it switches behavior when x goes to the left of 2. So this parabola, even though yes, it would be a parabola that would come down here and make a U, we're not going to be able to see this piece of the parabola because it switches behavior at x is 2. Now, we'll let you get away with just doing 2 points as long as you bring some pre-acquired knowledge with you. This is shaped like a parabola, so it would be coming up here curving. Don't draw this as a straight line. Make it somewhat curving like a parabola would. up in that direction. And again, nothing would ever stop it from changing that direction because x continues on for every single number bigger than 2. There's a picture of what this graph would look like. All right, let's have a look at another one. So this one's got some more pieces to it. It's got 4 pieces to it. So let's start here and let's do some function notation first. Let's start with f at -1. If x is equal to -1, have a look up here and see where we would be. There's a typo in this actually. This should say less than, no, sorry, I'm wrong. We're good. If x was at -1, that's a number that's less than 1. It's here. So I would put -1 in x in this piece of the function. 2, take away a -1 squared. That would be 2, take away 1. That would give me 1. So f at -1, that means the y value when x is -1 in this graph should turn out to be 1. Let's do f at 1. F at 1. Well, figure out where you are. Now, this one's going to be easy because at the very instant when x equals 1, it says right here, if x is equal to 1 and x is equal to 1, then the y value is 3. I don't got to do any work. That one's a 3. F at 3. So if x is equal to the number 3, f at 3. Put it underneath here. So if x is equal to 3, it would be here because this is when x is less than or equal to 3. So I'm going to put 3 in for x here. 2, oops, multiplied by 3, subtract 1, 6 subtract 1, 5. So f at 3 is 5. F at 2. Now, where would 2 fit into these intervals? 2 is a number that's somewhere between 1 and 3. Therefore, I would put it into the same piece of the function again. Just put it over here. F at 2. I'm going to put x in as 2, so it's 2 multiplied by 2 minus 1. 4 subtract 1 is 3. There are a few function notation questions using a piecewise function as our base function to work off of. Now, I want to draw this. So I'm going to go to a nice clean page so I got some room. This one's a little bit more elaborate than the last one. Where's my graph now? Edit. Paste. Alright, so I'll just get this shrunk down a little bit and put it over here. Before we start, kind of look things over and say, what am I dealing with here? Parabola. X is a number, and I get a number, that's an ordered pair. It's just a single point on the graph. 2x minus 1, so that's linear. And here's another quadratic. So I'm going to number these 1, 2, 3, 4, and I'll just kind of put them over here. So number 1 is the function y equals 2 take away x squared. Well, it opens down. It's a quadratic. It has its vertex at, so there's nothing added or subtracted with the x here, so it's 0. It's got a plus 2, so imagine that this was y equals, just to put it in vertex form. There it is in vertex form. So it's going to move it up 2. There's your vertex. Now the nice thing is this time, the vertex, that's a point I can use because the x value, which is 0, is less than 1. So there's a point that's going to be part of our graph. And now I need to know where this graph is at that number as well. So I'm going to fill in 1. 2 take away 1 squared would give me 1. There's all I need to get my sketch of 1. That's enough information and clues, so I'll just leave that one for a second. Number 2, this one's really easy. It says if x is 1, the y value is 3. That's, in a fancy way, telling you that has to be true. It's just a dot on the graph at 1, 3. That one's done. I should have switched colors here. Let's go to number 3. This is linear. So if it's linear, it's the graph, in this case, 2x take away 1. Now notice this one has 2 boundaries. So what I have to do is figure out where it is at the 2 ends of the line. So I'm going to go x and y, fill in the left end and the right end. I got those from here, 1 and 3. When x is 1, 2 times 1 is 2, 2 take away 1 is 1. when x is 3. 2 times 3 is 6. 6 take away 1 is 5. 1, 1 will be open circle. 3, 5 will be closed because of the equal sign here. That's number 3 done. Number 4, y equals x subtract 4 all to be squared. So this is another quadratic. This one opens up, so it opens up. It has its vertex at positive 4. Now there's no number out here after. This is a bad square, that's squared. There's no number out here after it, so that would mean that it is at 4, 0. I need one more point. Once you get, I can use that point because it's more than 3. The x value here is more than 3. So there's one point I can use. I need at least one more. I'm going to, and I have to use my boundary number. So let's go x, comma y. Let's put 3 in here. 3 take away 4 is negative 1. Square negative 1, I get positive 1. Now, put all of those 4 together on one grid. Let's look things over. The biggest y value I see here anywhere is 5. The x's are all positive, so I don't need too much in the negative scale. I got no negative y's, so my graph can be pretty much dominant in the first quadrant. So I'm going to come down, across. One, 2, 3, 4, 5. So there's x or y is 5. 1, 2, 3, 4. So there's 4. There's 2. Try and eyeball these to get them roughly the same. You don't have, they don't have to be perfect, but somewhat similar to the size of your scale on each axis. Okay, so let's start with number 1. I know it's a parabola, I know it opens down, and I know the vertex is at 0, 2, and I'm allowed to actually, in this case, put the vertex because the x-coordinate of the vertex is less than 1. So let's put that point up, 0, 2. Now don't lose track of what it is. This is the vertex. So 0, and we'll keep it in black. 0, 2 is the vertex. Now that's not your boundary number, so it's always going to be filled in. Now I got to go to my boundary. My boundary is 1, 1. Now I got to figure out whether it's going to be represented with an open or a closed circle at the edge of this. There's no equal sign, so it's going to be an open circle. 1, 1 will be an open circle on our graph. 1, 1, open circle on our graph. So you've got this point, which is the vertex. You've got this point, which is kind of the boundary where it's going to cut off and start to do something different. We'll then use symmetry because it's a parabola that opens down. Here's what happens. Students that don't have enough prerequisite skills, they'll get here and they'll draw a straight line out through this. It's not linear, it's a quadratic. That's the vertex, it opens down. So use symmetry. Over 1, down 1, over 1, down 1. Put a dot right there. And now make, as best you can, a parabola that goes forever toward the left. It's cut off here because of the interval ending there. There's graph 1 put on there, or piece 1 of the function. Well, here's an easy one. Piece 2 of the function is just the ordered pair 1, 3. So I'll put that in red, just so we can see each of the 4 pieces. So 1, 3 is a single dot on my graph. There's piece 2, done. Piece 3, 2x subtract 1. So it's linear. I've got my 2 endpoints. We said 1, 1 will be open because there's no equal sign. 3, 5 will be closed. 3, 5 will be closed because there is an equal sign. So let's go 1, 1, open circle. 1, 1 is open is already there. If it had told me to fill that in and it was open, filling it in would override what happened in the last interval. However, it's telling me to still keep it open. And then the other end of the line is at the point 3, 5, which we said we will fill in. So 3, 5 will be filled in. I should switch to a different color. So there's the end of that line. This was the other end of it. Straight edge. Connect those together. There's piece 3 of the function. And then last but not least, piece 4. It opens up, it's a quadratic, so we've got the vertex, which is at 4, 0. I'll put that on. Remember, we are able to use the vertex this time because it's in the interval. So 4 comma 0 is right there. The left edge of this parabola is at when x is 3. So when x is 3, the y value is 1, and it would be an open circle. So I'm going to go to 3 comma 1 and put an open circle. Let me just back up to that for a second. Yep, so that's good. 3 comma 1, 3 comma 1, open. Use symmetry, over 1, up 1. I know it's a U-shaped graph, so it's not going to go down here. It's going to turn and go back up here. So I'll get another dot over there, and I'll get a graph that looks like that. And there you have the 4 different pieces of the function all sketched properly. The most common mistake students make is they have arrows and they keep these graphs all crisscrossing over top of each other. The only arrows are ever going to be at the left end when it goes forever and the right end. In between here in the middle, there's never going to be arrows where these pieces of the graph kind of run over top of each other. They'll always kind of stop, and there may be a gap like there is here, or a kind of a jumping thing here, which in calculus we'll talk about what these situations are. And that's kind of what this is. It's laying the groundwork for a section in calculus on what's called continuity and examining functions for where there's gaps and holes in them. However, we're expected when we start to analyze that we know how to draw a piecewise function, which is why we're studying it in Pre-Calc 12a. All right, I've got one more I think we'll look at. So let's look at this one. So this one has some function evaluation down here. So it wants us to do 4 times f at negative 1 plus f at 0 take away 5 multiplied by the value of f at 4. I'm going to do these 3 calculations just over here to the side so you can see them. Let's do f at negative 1, meaning if I put negative 1 in for x, so negative 1 plus 3, that's 2, squared is 4, with a negative in front, it's going to be negative 4, add 2, f at 1 is going to get replaced with the number negative 2. All right, and the reason I put it in there is because less than or equal to negative 1. F at 0. 0 would be somewhere between negative 1 and 2, which is what this interval means. Any number between negative 1 and 2, which would be 0, that's in between those, the answer is always 1. So f at 0 is equal to the number 1. F at 4, so now I have a number that is more than 2. If the x value is more than 2, I'd use this piece of the function. So that would be 2 multiplied by 4. I'm not going to show it, we're doing it in our head here, sorry. So 2 times 4 is 8. 8 take away 3 would be 5. Go over to here. So this is just what they call a scalar. It's just a number, so leave the 4. Replace f at negative 1 with what you got for the answer for f at negative 1, which is negative 2. Replace f at 0 with what you got for an answer, which was 1. 5 is just another scalar, so a number you're going to multiply by. F at 4, I got 5 as the answer. And now we'll just calculate this. So this is going to give us negative 8 plus 1, take away 25, which will give me negative 33 plus 1. The answer will be negative 32 for that expression. All right, let's graph it. So I've got a quadratic opening down, vertex negative 3, 2, and it does this if x is less than negative 1. So that's going to be fine. This is just the line y equals 1. So let's, I don't know if I can, let's just take a picture of this. Where's my screen capture? I don't think I have it on my toolbar. I don't. All right, so we'll have to go by memory here. I'll put that on later. If I want to look at the 3 pieces, so the 3 pieces of this function are y equals negative x plus 3 squared plus 2. So just to put some information, you don't have to write this all down. If you can keep track of it in your head, that's fine. So it opens down. It has its vertex at negative 3, 2. And the edge of it is x is less than or equal to negative 1, so I need to know where it is at the boundary. put in -1 in here. -1 plus 3 is 2, squared is 4, -4 plus 2. Actually, we'd already done that up here. I knew it should be -2. There's piece 1, looked after. Piece 2 of the function. Let's do it in red. Piece 2 should be fairly straightforward. Piece 2 is just the line y equals 1. That's a horizontal line passing through 1, and it does that from -1 to 2. Open circle at -1, filled in circle at 2. Back to this one for a second. We said that one would be closed in because it's got an equal sign. Piece 3 of the function is another linear. So I'll just put it here beside it maybe. So piece 3. I need a couple of points to help me draw the line, so I use this one always. Boundary number, 2 times 2 is 4, 4 take away 3 is 1. And now you have to pick another number that's in the interval. So I'm going to go with 3. 2 times 3 is 6, 6 take away 3 is 3. Alright, so I've got number 1, which is a parabola opening down and closing it off at the x value -1. So let's see what I've got. Vertex. So we're going to go -1, -2, -3, -4. So there's -3. Y values go up as high as 3. So 1, 2, 3, 4. I'll put an extra one up there. We'll go this way. 1, 2, 3. Say 4 that way. I've got a negative. So let's go down to -3. And here's my graph. Alright, vertex -3 and 2, which is in the interval, less than negative or equal to -1, so I can include that point, -3, 2. My boundary number is -1, -2, so -1, -2, and that was closed in, right? Closed in because there's an equal sign. So -1, -2 will have a closed in dot. -1, -2, close it in. Now it's a parabola, so there's another point over here somewhere. Now let's use symmetry. I went 2 places right, and I'm down here at -2. 2 places left. So that other point is going to go 2 to the left and down at the same height as this one. So I should have another, so 2 to the left will be at -5. Put me down here. And this parabola would start here, go up, down, and there, that would be the top piece of the function. The middle piece of the function, which is just a straight line, we said, that's y equals 1. Now I just got to determine, so I'm going to, from -1 over to 2, open on the left end, closed because of the equal sign in front of the 2. So between -1 and 2, it's a horizontal line running through 1. So -1 through 1. We said this end is open. And then it goes over as far as 2. I think it was 2. Double check. Yep, 2. And it's closed on that end. So at 2, it's also up at the same horizontal line. And then it should go straight across through there. That's piece 2. Piece 3 of the function is linear. The first point I used was 2, 1, which would be an open point on the graph because there's no equal sign. So let's go to 2, 1 and put an open circle. 2, 1. Now I'm glad this example popped up because you say, well, it's already closed in. It can't be both. It can't be open and closed. If it got closed in earlier, there's nothing I can do about it. It's already closed in. So I'm still going to use that point, but it's closed in from an earlier interval in the graph. And then I'm going to go to my second point, which is 3, 3. 3, 3. It should be there. And now it's linear, which would be a line. So there's your piecewise function sketched. Okay, so that's all I'm going to do in this video. Just a quick rundown of what a piecewise function entails in terms of using it and determining which piece of the function to use. And then I've gone through how to sketch 3 of them. So I'll give you a few of these to practice before we move on to our next section in transformations of functions. Thank you and best of luck. Reach out if you have any problems or concerns.